Up until this point, we've looked at what are called congruent figures, which from the past we've seen they are figures with congruent corresponding, whatever it is, a little bit, with corresponding sides and angles. That are congruent. Congruent figures are figures that have congruent sides and congruent angles, like they correspond. That's what we kind of focused our study on so far. We're actually going to generalize this a little bit more and look at figures that are called similar. Similar is not a vague term in math. Similar is not vague. It's very specific. It's not just, it doesn't just say that they kind of look alike or that they're like kind of the same. Similar figures has a very specific definition. This definition is as follows. It's figures with proportional corresponding sides and congruent corresponding angles. Okay. We're going to generalize a little bit more from congruent. Congruent is a specific case of similar figures. Notice that in both of these, the angles are congruent. They have the same general shape. They look alike. However, for congruent, the side lengths must also be the same measures. Versus similar figures, we can generalize a little bit more, and maybe they don't need to necessarily be the same, but they can be proportional, or their ratios of any corresponding side lengths are always the same. Congruent figures is actually just a very specific case of similarity where the proportion between the two figures, the proportions of the side lengths is just 1 to 1, where they're the same. But similar, we can talk about figures when they change the relative size. When we zoom in, zoom out, stretch or shrink them, while keeping the same shape, by keeping the angles the same measure. And we're going to start by looking just in general what it means with similarity. Notation, the squiggly line is called a tilde, is the notation for similar. Okay. That's not good. Is the notation for similar. The little tilde is the notation for similar. We know it's the same thing you put over top of congruent, the equal sign for congruency. So if I tell you two figures here are similar, we can do a couple things. You should be able to list the congruent angles, and we should be able to list the congruent. We should be able to list the proportional sides, or write a ratio of sides that are equal. Now, someone last hour actually pointed out that my similarity statement here is actually wrong, which he didn't do absolutely right. The similarity statement here should actually read as follows: C, D, E, F is similar to M, J, A, L. Would be a better similarity statement. Just like a congruent statement, we write these in such a way that the corresponding angles match up, the corresponding angles correspond in the statement itself, and then all the corresponding side lengths we could build by taking pairs of the letter pairs in the same spots in our similarity statement. So just like a congruent statement, the similarity statement tells you a ton about the figure. It tells you where all the corresponding parts are, both angles and sides. So for example, listing the pairs of congruent angles. For my similarity statement, I should have angle C is congruent to angle M. I should have angle D is congruent to angle J. What would be two other congruent angle pairs, just from the similarity statement? Page was 1. And Kate, what was the other one?
Angle F is congruent to angle L.
These figures have the same, the angle measures, corresponding angle measures should be the same. We can also write, we should also be able to set up some side length ratios that are all equal, based on the similarity statement as well. As before, we had a bunch of, congruence, we had sides that were congruent or equal in measure for a congruent statement. For a similarity statement, we can't get that, but we can get angles that are, or side lengths, excuse me, that are proportional. So from my similarity statement, without even looking at the diagram, assuming this is correct, I should be able to say the ratio of CD to MJ the ratio of this side pair should be the same as a ratio of, say, another corresponding side pair. So how about EF and KL? Notice since my side lengths are proportional, they're not equal. So I can't just get that CD is equal to MJ. But I do know that their ratio is the same. They're proportional. So if I say CD to MJ, that ratio should be the same as any other ratio of side lengths. So CD to MJ should be the same ratio from, say, EF to KL. Would anyone like to take a stab at what another ratio I could set up would be? Isabel?
Proportional to JJ.
DE to JK. And there should be one more. So I've got CD and MJ. I've got EF and KL. We've got DE and KL. There's one more that we get, Kelsey. CF over. These four proportions, these four ratios should all be equal. Okay. So if I wanted to find, say, a missing piece, I could just pick any two of them, and then I'd have a proportion I could say cross multiply and solve to find the missing part. Okay. I haven't given you any numbers, so it's kind of difficult to do that for this example, but these are some ratios we can set up in a proportion. Okay. We're going to talk a lot about this thing called a scale factor, which you've seen in like maps and stuff. Maps are just similar figures. So like an overview of the Earth versus a similar figure on a plane. The scale factor simply is the number that connects the two ratios, the two figures, or more or less it's what you have to multiply. One figure's lengths by to get to the others. Now, you've seen scale factors on maps before. It's the same game here. So we're just, if I want to ask you what the scale factor is to go from one figure to the other, that's asking you what do I have to multiply any length on this side by to get to its corresponding side of the other. To calculate that, it's actually not so bad. So if I'm going to actually give these a label. I'm going to call this figure A. I call this figure B. Even though there's actually the point A and B there. I'm going to call this the first figure and the second figure. I want to find the scale factor, SF, from A to B. If I want to calculate very efficiently how do I go from A to B, I'm going to find the ratio of the lengths of any part in B to its corresponding part in A. If I want to find the scale factor from where I start to where I'm going, I'll divide where I'm ending by where I started. That makes sense. So for example, I want to know what the scale factor is to go from triangle A to triangle B. I'll pick a part in B and divide it by its corresponding part in A. For example, I could pick say 10 to its corresponding part in the first figure, which is 5. Or I should be able to pick say 8 and divide it by its corresponding part, which is 4, and similarly 6 to 3. Notice that these things are all the same. These are all 2. So the scale factor to go from A to B is 2. I'll multiply anything in A by 2, and I get B.
So if you have the scale factor, and if you take one, for example, times on the other side, and if you use that and divide it by a bigger number, so your triangle, and times it by the other one, would you get the other side? Because I was never seen that in homework.
So then the scale factor changes if I want to go from B to A. If I want to find the scale factor from my second figure to the first, then I want to take where I'm ending and divide by where I'm going, where I started.
But I just noticed that,
the scale factor going from A to B is 2 to 1. But the scale factor coming in this direction from B to A is 1 to 2. So it's saying that I'll take whatever number here and multiply it by a half, and that'll get me this figure. Okay, so the scale factor is not static. It'll actually change based on where you're starting, where you're ending.
But I noticed if you put, since
Also, one main way to check if figures are similar at all is if they have the same scale factor for every corresponding pair. If they don't, then the figures aren't similar. So for example, if I found, say, the scale factor of, say, the short side of this rectangle to this short side would be 6 to 3, is that equal to the proportion of the other sides of, say, 8 to 6? This is 2 over 1. This is, what, 4 over 3?
Yeah.
Yeah, those are not equal. So these are not similar. Okay. You end up here with a scale with 2 proportions that aren't equal. So the side lengths aren't proportional.
you cross multiply.
Alright, so now they're similar, we can use that idea of similarity statement and actually find some missing pieces. And this is kind of where we're headed in the next, for the rest of this chapter. Is to be able to take some similarity statements and then create some proportions. So for example, if triangle STU is similar to PQR, that means that ST over PQ better be the same as, say, SU over PR, which also must be the same as TU over QR. That's not really important because we don't know anything about those side lengths. Or if you substitute in the values you know, you get 6 over 4 is 12 over x. And you can find x. Cross multiply, divide, you end up with, what, 9? Or is it 8? 8, yeah, sorry, 8, not 9. 6x equals 48 x. See? Same game here. If I give you some, boy, I think I miss this. Yeah, well, we're gonna go. I'm gonna add a caveat here that these are rectangles. Rectangles having the same opposite sides. So if this is x, then this is also x. Otherwise, my similarity statement doesn't really help us. You wouldn't normally be able to claim that unless I told you or was printing the problem, so don't. Whatever. Anyways, my similarity statements, I could say, how about ED? ED is to KL, or 8 to 12. ED is to KL, as CE is to JK. CE is to JK. And you can again cross multiply itself. I'm going to state this. I'm going to bypass this story problem. So we'll skip this for here. I believe there's an example in the book that's very similar to this. I just want to state the perimeter, which is simply that for similar figures, the perimeters are proportional to the sides. So if you just add up all the side lengths, you get the same ratio as if you just take any one pair of the sides. Okay. So like in the example, you can actually, without knowing what the perimeter is and without getting any of the individual side lengths of the second pool, you can actually find its perimeter without even knowing the individual side lengths. Because we can find the ratio of the sides we can set up a ratio involving any one side length and go directly to its perimeter without having to do much other calculations. Okay. I do want to skip that section. Skip that and we'll get to the last idea here. Is that the last idea is the corresponding side lengths in similar corresponding lengths in similar polygons is that any segment in similar polygons are proportional. So not just the side lengths, but as we saw last chapter when we talked triangles, we drew in altitudes. Corresponding altitudes are proportional. Corresponding medians are proportional. Corresponding, perpendicular bisections really have sense in triangles. They don't actually are with it. But any corresponding segment that you could draw in a triangle or in a figure in general are also proportional if you have similar. So, like for example, if I drew the medians of these triangles, and I know that those triangles are similar, then if I knew, say, the same ratio of, say, a big side length or the ratio of AB to DE needs to be the same as Y to 16. The corresponding medians should also be proportional. So you can say 27 to 36 is the same as Y to 16. and we should be able to calculate y in this fashion. Okay, not just the side lengths, but any of these pieces. And this is kind of the jumping off point for the rest of the chapter. So we're going to focus in on triangles and similar triangles and look at how we can prove they're similar, how we can, once we know triangles are similar, what does that tell us about the side lengths and ratios and stuff from there.